Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take the class of electromagnetic wave, subject code EC501. Today's topic is about the vector calculus. In previous slides, we have discussed line integral, surface integral, volume integrals. We have described what is the Dale operator, what is the function, what is the significance of divergence of vector, and in this lecture we are going to describe what is curl of a vector, what is the significance of a curl of a vector, what is the Laplacian operator, and at the end of this lecture we will put an end to the vector calculus topic, and from the next lecture we are going to talk about basic laws of electromagnetism and Maxwell equation. So let's start the class. So first topic that we are going to discuss is about the curl of a vector. Now what is the curl of a vector? The curl of a vector A, the curl of a vector A is an axial or rotational vector whose magnitude is the maximum circulation of A per unit area tends to 0, and whose direction is the normal direction of the area when the area is oriented so as to make the circulation maximum. So this is the physical basic definition of a curl of a vector. Now we are going to realize how it works. Now the curl of a vector is basically, now if we take a close look, that curl of a vector can be described as del cross A. Now in case of divergence theorem, or in case of divergence of vector, the divergence of vector is represented as the del dot A, and that the value is that divergence of vector describe the net outward flux of a specific vector in a continuous space region, suppose S, per unit volume. Net outward flux per unit volume in case of a specific region of a specific vector. Now in case of curl, what we have here is that del cross A is the curl of a vector. Now it has been mathematically represented as that A dot dl, or A dot, the surface integral of the closed loop integral of A dot dl will be divided by the del S. It means the net. Now what is the significance of A dot dl? What is the significance of A dot dl? A dot dl is basically, now A dot dl is basically represent the line integral. Now if we take a line integral of a closed path, it will provide us the surface integral of the specific vector. Now here the vector is A. Now this value has been divided by the del S. Del S is the infinitesimal small value of S, or the surface area. Now the significance of curl of vector A can be determined or can be described using this mathematical representation. Now if we go back to the definition here, that the curl of a vector A is an axial vector whose magnitude, axial vector or rotational vector whose magnitude is the maximum circulation of A per unit area tends to 0, and whose direction is the normal direction of the area when the area is oriented so as to make the circulation maximum. It means, first of all, the magnitude A is an axial vector whose magnitude is the maximum circulation of A per unit area. Now for unit area we have divided the line integral of that closed path by del S. Now by dividing del S we will get the per unit area value of the maximum circulation of this value. Now the curl of a vector, in case of curl of a vector, the direction will be normal to that surface. Now here, as we have taken a closed integral of A dot dl, it means the surface is closed. We have a surface. Now the direction of that vector, the curl of that vector will always be normal to the surface. Now suppose this surface we have taken down in this surface, this vector A is continuous in this specific surface. Now if we take a closed loop integral of that vector A, we will get a we will get the resultant of a surface integral. Now if we divide that value by the total surface area, we will get the maximum value in the net maximum value of the circulation per unit area. That is what we have described in the mathematical representation, and that is the explanation of the definition. Now curl of a vector A is an axial vector because it is along the axial vector whose magnitude is the maximum circulation of A per unit area. Maximum circulation of A. The magnitude is the maximum circulation of A per unit area, and the direction will be normal to the area, oriented so as to make the circulation maximum. So this is the mathematical representation of curl of a vector, and this is A suffix n represent the direction of the vector which is normal to the surface. Now suppose this is a closed vector and this is a closed surface. Now A dot dl will be described as A to B. Now this is a closed surface. Okay, closed surface. It has started from A to B. Now we will take an integral of A to B, then B to C, then C to D, and again D to A. Now this is the direction of that specific vector. It is now if this is a closed path, then this is a circular the whole vector direction of the vector in a circular motion or in a circulation. This is not in circular motion, this is in circulation. Now this is the circulation. Now if you take a closed surface closed integral of that A dot dl vector, and we divide that the value of that surface integral by the total surface area, we will get the value of the curl of a vector, and the direction of the vector will be normal to that normal to that surface. Now suppose this is the point P, this is the point P, and this is the vector that is working in the path. This is d1, this is dz. Now if it is surface integral, we get this value, and this is the value. This is the curl of vector. The curl of vector practically used in solenoid. In electromagnetism, it has a very much use. It is a great use in solenoid. In case of solenoid, we will put an element which has a magnetic force, and will work and the vector is worked as a circulation, and the resultant vector, the curl of a vector, will provide us a vector. The direction of the vector is normal to the surface. That's why the curl of the significance of the curl of vector is in the magnetism. In magnetic force, in case of magnetic field, the curl of vector has a greater significance. Now, as because it's a curl vector, so it can be described using in case of Cartesian coordinate system, it can be described in del cross A, where A suffix x in del of del x, and this is it is along the x-axis, it is along the y-axis, and it is along the z-axis, and it can be described using this. We have already described that how we use matrix multiplication in case of cross vector. Now del cross A, so you can represent using the matrix form for Cartesian coordinate system, and for circular cylindrical coordinate system, we use the same format, but with few differences. It's 1 by rho, and this is here rho fi has been we will put that value, and again using matrix multiplication format, we can determine the value of curl of a vector in circular cylindrical coordinate system, and same will be applicable for spherical coordinate system, where del cross A is equal to 1 by r square sin theta, a suffix r, a suffix theta, a suffix phi. Along the a suffix r, the value of along a suffix along r, sorry, along r, value will be del r, and this a suffix r, and this r a theta, this r sin theta a phi. Using that we can determine the value of determine the curl of a vector in spherical coordinate. Let's go to the next slide, and that is Stokes theorem. Now, what is the Stokes theorem really define? The circulation of a vector field A, the circulation of a vector field A around a closed path L is equal to the surface integral of the curl of A over the open surface S bounded by L, that A and curl of A are continuous on S. Practically, what it really defines is that if we go back to the definition of curl of a vector, the curl of a vector is suggesting that the curl of a vector is basically nothing but a closed contour integral of a vector A, right? It is in a closed path. Now, if we divide that with the total surface area, we will get the curl of a vector, which is in direction normal to the surface, and the maximum, and with the circulation of maximum value we will get curl of vector. Now suppose we have provided with A dot dl. Now A dot dl is, now if this specific mathematical operation represent a closed surface, the closed integral, it suggests a closed surface. Suppose this is suppose this is a path. Suppose this is a path. If we take a line integral of vector A along this path, along this line from A to B, this will be a line integral. Now it's a line integral. Now suppose we take the total surface. If we take the line integral along the path from A to B, B to C, C to D, and D to A. Now the whole path is closed. Now if we take the line integral of the closed path, it will basically provide us a surface. A closed path basically represents a surface. So if we take a closed integral of vector A, we will get a surface. Now we will get a surface integral. So the curl of a vector is also basically the surface integral, is basically providing the representation of a surface, but the vector value of the vector in case of in circular motion, the value of the vector is maximum and the direction of the vector will be normal to the surface. That is what Stokes theorem basically states, that the circulation of a vector field A around the closed path A is equal to the surface integral of the curl of a vector. The surface integral of a curl of a vector is basically is equal to the closed path integral of the vector field A. Now, if the vector A is, suppose there is a the vector, there is a force acting upon a particle, and because of that force, that particle is moving. Now, if that particle is moving around a closed path, it means it is in a circular motion. Now, if we take the line integral of that specific vector, what we will get? We will get a basically a surface integral, and the circulation of the vector field, and the direction will be normal to the surface. Now, if we take a curl of that specific vector, that vector f, and we take a surface integral of that specific curl of that vector, we will get this value. So both this value and this value will provide us with the same mathematical representation, where the magnitude and the direction, using this mathematical operation, we can get the same representation of that specific vector, where it will provide us the maximum value of the circulation of that specific vector A, and the direction will be also, the direction which provided by these two mathematical operations will be same. Now this is Stokes theorem. Now Stokes theorem is provided as a closed surface, and the value of ds is normal to the specific surface. Now if this is the closed path, now if we take a if you take a line integral of a closed path, it will provide us a surface. Now the surface integral of curl is also providing the same result. That is what the Stokes theorem basically states. This is the pictorial depiction of Stokes theorem. This is the basic definition of Stokes theorem. Now, the Laplacian of a scalar. What is the significance of Laplacian of a scalar? What is the Laplacian of scalar field is? The Laplacian of a scalar field is written as del square V. Now, del is basically the del operator. Basically, the del operator, where Laplacian V is del square V is del dot del V. This is the important factor. The del square V is basically del dot del V. It means del is representing this del of del x s of x, del of del y s of x y, plus del of del z s of x y. This is the del operator, and this is basically gradient of a scalar function that we have already discussed. The gradient of a scalar function is basically a vector field. It means that this gradient of a scalar, this is a vector quantity. Yes, this physical quantity represent a vector. Now this is a vector. Now after that we will take a dot product of the del operator and this vector field, and it means basically if we consecutively take a grad of a scalar function and then divergence of the specific vector quantity that has been derived from the gradient of a scalar function, if we take a divergence of that specific vector quantity, we will get a Laplacian of a scalar field. That's why it is known as the Laplacian of a scalar field. Now Laplacian of a scalar, how it has been described? Let's see. The Laplacian of a scalar field V, written as del square V, is the divergence of the gradient of V. It is another scalar field. Practically that is what that. Now there is a basic distinction between these three things. First, if we take a gradient of a scalar function, it is providing a vector quantity. Now if we take a divergence of a vector quantity, it will provide you a scalar function. Now if we take a divergence of a scalar field, divergence of a gradient of a V, and gradient of a V will provide you a vector quantity. Now if we take a divergence of a vector quantity, it will provide you another scalar field. That's what the Laplacian is basically. The significance of Laplacian is this. And in Cartesian coordinate system, Laplacian value will be del dot del V, del square V, and this is the del operator, and this is the gradient of that value V. And if you take a del square V, it is basically del square V del x square plus del square V del y square and plus del square V del z square. A scalar field V is said to be harmonic in a given region if its Laplacian vanishes in the region, and this is the Laplacian equation. Del square V is equal to significant. Now if we repeat it, that what we get here, that a scalar field V is said to be harmonic in a given region if its Laplacian vanishes in the region. It means, suppose we take a gradient of a vector V, gradient of function V, gradient of a scalar, gradient of a scalar field, it will provide us with a vector field. Now if we take a divergence of the specific vector field and the value is resultant in 0, then we can say that a scalar field V is said to, then this scalar field V will be harmonic motion. If we take a grad of a scalar field, it will provide a vector field. Now that vector field, if the divergence of the vector field provides us a 0 value, then we can say that specific scalar field V is in a harmonic motion. It's in a harmonic motion. To define or mathematically express the harmonic motion, we use the Laplacian equation. If the Laplacian equation provides you a 0, the scalar field V will be can be said as a harmonic motion. So that is the significance of Laplacian of scalar. Okay. So let's go to the lecture. Now the Laplacian of a scalar for Cartesian coordinate system, we got this, and for cylindrical coordinate system, the value of Laplacian is 1 by rho del of del rho del V del rho plus 1 by rho square into del square V by del phi plus del square V by del Z square. This is the circular cylindrical coordinate system. And for spherical coordinate system, the Laplacian of a scalar is 1 by r square del of del r square del v by del r plus 1 by r square sin theta into del of del theta sin theta into del v by del theta plus 1 by r square sin square theta into del square v by del phi square. So this is the Laplacian of a scalar for spherical coordinate. So for Cartesian coordinate, the value of Laplacian scalar Laplacian of scalar is this. For circular cylindrical coordinate, the value is this, and for spherical coordinate, the value is this. And these are the example that you can try in home. These are very simple. That suppose and we can know from this that v is equal to e minus z sin 2x cos hy. It means it is in a Cartesian coordinate system. So we will use this value as an operator for Laplacian. And for rho square z cos 2 phi, that function we have also introduced earlier, that here del phi z are the three coordinates for circular cylindrical coordinate system. So for that specific function we will use circular cylindrical coordinate system. And for tan r sin square theta cos phi, we will have spherical coordinate system. 1 by r square del of del r square del v by del r plus 1 by r square. This function will be used. So up to this, what we have learned is that Laplacian of scalar, we have understood line integral, we have understood surface integral, we have understood volume integral, how it works, how the del operator works. Del operator had different it operates differently in Cartesian coordinate system, in spherical coordinate system, and in circular cylindrical coordinate system. Now using del operator, we can find the gradient of a scalar field, and the gradient of a scalar field is a vector quantity. Now divergence of a vector field is a scalar quantity. Now we have understood what is the divergence of a vector field, we have understood what is the divergence theorem, we have understood what is the curl of a vector, and we have understood the Stokes theorem. And the Stokes theorem basically represents the closed integral of a displacement function, basically a vector. Suppose is integration L a dot dl is equal to basically surface integral of the curl of a vector, the same specific vector. So that is the Stokes theorem. And in case of divergence theorem, it basically a divergence of a vector, the divergence of a vector is basically providing the net outward flux per unit volume. So that is the divergence, and this is the divergence of a vector. And the divergence theorem basically providing the option is that suppose we take a surface integral of a specific vector, it will basically equal to the volume integral of the divergence. Volume integral of the divergence of that vector is basically equal to the surface integral of that specific vector in that specific closed surface. So that's how we have ended. This is the examples. We have ended our lecture here. We have understood different kind of functions. What is divergence theorem, what is Stokes theorem, what is curl of a vector, what is divergence of a vector, what is gradient of a vector, what is del operator, and what is Laplacian of a scalar field. So that's why, and Laplacian of a scalar field basically used to understand the scalar field, that is harmonic or not. To understand the scalar field, you use this kind of mathematical representation or operation to understand whether that vector field is harmonic or not. So with this we will end this class today. Thank you.